So in this first video we'll be talking about random variables, probably abbreviate that in future videos as just RV. And specifically we'll talk about how we're going to make computers make random numbers for us. And that's kind of a lie, right? Because computers are inherently deterministic. They can only do exactly what we tell them to do. So instead we're going to talk about three types of randomness. So we could say of random, and those are true randomness, pseudo, and quasi-randomness, right? So if we look at the first one, that's true randomness, then that's, well, it is what it says, right? It's something which is truly random. It's something like radiation Geiger counters or atmospheric noise creating radio waves, or I've even seen examples online of people pointing digital cameras at lava lamps and looking at the sort of output they get. If you want an example, you can take the radio waves one. Then if you go to random.org, then they'll actually supply you with some truly random numbers, and if you're a big organization, then you can buy them. So this might be used for something like a lottery or gambling, right? So the pro of this type of random numbers, that's the true random numbers, is of course that, well, it's random. It's exactly what it's supposed to be, right? At least as far as physicists can tell us. The cons or the drawbacks is that it's probably gonna be slow. It's probably gonna be really expensive. It takes a lot of physical equipment to get these numbers, and it's not gonna be reproducible. So if you calculate something based on this and then you want to do it again, well, you're gonna get a different number, and that might not always be desirable. For example, if you want someone to be able to replicate the numbers you're getting, right? But really the main drawback is that it's slow. So that takes us to the second type of random numbers, which is pseudo randomness, and this will be our focus, right? And an example of this is something like the digits of pi. So that would be 3.14159265 it goes on forever, right? Then if we want to take these random digits, and as far as people can tell, this is actually a pretty good source of randomness. So just say here that digits of pi are actually a pretty good source. And what I mean by pretty good is that it passes a lot of tests that we can use to see are these numbers, these digits here, are they independent and are they uniformly distributed, right? And then, based on these numbers here, then we can go something like 0.14, 0.15, 0.92, and so on, right? And you'll get some random numbers between 0 and 1. Of course, in practice, you might take more digits than just in the first two digits. And these kinds of methods, not just the digits of pi, but these methods in general, are going to be fast. You're going to be able to use your asymptotic theory. So that's something like laws of large numbers and your central limit theorems. And critically, you're going to be able to have reproducible results. But of course, it is inherently deterministic, right? So it's not really random, right? So we're sort of deviating from what we actually want, but we can still use the mathematical tools. So that's mostly okay. And then the last type is what's called quasi-random numbers, and we're not going to spend too much time on those here, but we'll use them later on for variance reduction. Right? And just to give sort of an illustrative example of what these are all about, if we have an example for a coin, then we might take the quasi-random numbers as 0, 1, 0, 1, 0, and so on, right? So, well, this is still going to be fast, it's still going to be reproducible, and it's actually going to have a lower variance than the pseudo-random numbers, right? Because you have no chance of getting a bad sample, right? So, let's say no simulation variability. Right, so you're going to have a lower variance of your output compared to using pseudo-random numbers, but you're not going to be having any asymptotic theory, and it's going to be deterministic, just like the pseudo-random numbers, right? But the main point is you lose your asymptotic theory, the laws of large numbers, your central limit theorems, but you gain a lower variance. Okay, so if we go on and continue with the random variable generation, that's going to be the pseudo-random variable generation, then throughout this course, and certainly in all textbooks, it's pretty standard to assume that we can draw what's called uniforms, right? That's ID standard uniform. So we might write that something like U, which follows the standard uniform distribution. We'll call it ID, right? So it's a key assumption that we'll always be able to draw these quickly and independently. And the way we do this is by using a random number generator, usually called an RNG. Right? And just to sort of give an example of the properties of these methods without going into too many details, I'm just gonna go through an example of a really bad one, right? Also a pretty old one. So this is the middle square method, which was invented in 1949, I think it was, from von Neumann. And it's very simple. It only has 3 steps. So first you set some n-digit seed, right? And then you square the seed, so you raise it to the power of 2. Then you add leading zeros until you have 2 n digits, right? And then you use the middle n digits as output from your algorithm as the first random number, and then you also use it as a seed, so you can iterate back to the first step again, right? And let's just see an example of me going through that. So for example, for n equals to 4, we might select an initial seed of 540. So note I added a 0 in front, so we have the 4 digits. Well, what does this give us? It gives us, what is it, 291,600, right? So now we've squared it. This gives us this number. But then we see, okay, we only have 6 digits, so we have to add 2 zeros, 2 leading zeros here, to get to the 2 n digits. Well, and then in the next step we use the middle n digits, so that's going to be these here, these 4 digits here. Then we square them, and then we get the next number. That's going to be 5,030, which is going to get us to 3,009, which gets us actually back to 540, right? So this is sort of a little bit my fault, because I chose an initial bad seed, right? So I specifically chose this seed because it's really, really bad. It has a very small what's called a period. So that's the time before the number starts repeating, and then we'll just be caught in this loop over and over again, right? Now, luckily for us, if we look at something like Matlab's default method, or just, I think it's pretty much standard for all computer languages these days, it has a really long average period. So the average time before the numbers will start cycling back in, depending on the seed, is going to be something like 2 to the 19,000. Right? So it's just a huge number, right? And the default method, which is not this middle square one, is also going to be pretty fast, right? So I get something like 10 to the 7. That's 10 million uniforms in about 1 second. And that's on a pretty old computer, right? But note that the original seed you choose, it still matters, right? So if you're doing, say, if for example you're a bank and you're doing a big simulation to set aside capital, to determine how much capital you set aside to cover risk, well, then you might get an unlucky seed, right? And then you have to put away too much money, right? And you don't want that, so you might want to test with some different seeds. Okay, and now we're going to go to a Matlab coding example. So I'll just go over a brief code example in Matlab about what we just discussed. Here in this first line of code, I'm saying that for the uniform, that's unif, I want a random variable, R&D, and I want the low point and the high point of the distribution, that's 2 parameters, to be 0 and 1. So I want a random variable from the uniform distribution between 0 and 1. And we can see here that if I mark the code and press F9, I can get new random variables. I can also write RNG for random number generator and then 1, 2, 3, 4 to set a seed of 1, 2, 3, 4. If I mark this code and press F9 again, I can see that Matlab is using the type twister, that's the Mersenne twister, random number generator. It presently has a seed of 1, 2, 3, 4, an internal state, which I did not discuss earlier in the video, but this is what controls what random numbers gets out, and it's then changed at each iteration by the seed. And you can see it has an internal state, which is a vector, which is 625 long, of 32-bit characters. Okay? And we have set the seed to 1, 2, 3, 4. So if we ask for a random variable, I'm marking this piece of code here and press F9, we get 0.1915. We will then force the seed back to 1, 2, 3, 4 by marking the code and pressing F9 again. And then we'll get the same random number out again.